Welcome students to this next session on industrial metallurgy. This is session number 37 and we are covering a very interesting topic called the iron carbon system. I introduced this particular material system to you in the last session, and this is what we are going to cover in this particular session. The iron cementite equilibrium diagram, or what is also called the iron carbide equilibrium diagram. And before actually we go into the details of this diagram, first we'll see that what are the characteristic properties and meaning of various phases that are actually seen on this diagram. So just for your reference, I am showing over here the iron cementite diagram. See, this diagram is the iron cementite equilibrium diagram. Just this particular portion of the diagram has been magnified and showed out here at the top, and this portion of the diagram has again been magnified and shown over here. So before I actually get into the very details of this diagram with you, let us first see that what are the various phases that appear on this diagram, or in other words, whenever a iron carbon system is treated under strict conditions of equilibrium, what are the various phases that are seen in the iron carbon system. Now you see there are the first region that you can see, a single phase region, is the liquid solution. So this is a this region, so this is the liquidous line of the iron cementite diagram, and this is a single phase region which can take any whenever any iron carbon system is at a temperature such that it falls above this liquidous line, then it has got single phase in it, liquid solution of iron and carbon. Okay. But we are more interested in the phases that are observed in an iron carbon system when the iron carbon system is in the solid state. So one of the phases that exists in the iron carbon system is this alpha phase, which is popularly called ferrite. This is also called alpha ferrite or alpha solid solution. Then there is another single phase region, or there is another unique phase in the iron carbon system which is represented by gamma, and this is called austenite or gamma austenite, right? Then there is another single phase region which is designated as delta, or this is popularly called delta ferrite. And the last single phase region is this right extreme axis, which is representing a compound of iron and carbon containing 6.67 carbon and 93.33% iron. And when iron and carbon are present exactly in this ratio, the phase formed is called iron carbide or cementite, and that is represented by this vertical line. So students, in all there are 5 different single phase regions in the iron cementite diagram, or on the iron cementite diagram, or in the iron carbon system. I again repeat their name: liquid solution, ferrite, austenite, delta ferrite, iron carbide or cementite. So in the next slide, though I have just put down the headings only, but listen very carefully. I'll talk about what exactly these phases are. Are they solid solutions or are these intermediate phases? And I'll also discuss about some of the characteristic properties which these phases show. Okay. Now, the first phase that I'll discuss with you is called liquid solution. Is understood, and it's not of any importance to us, right? Because material system you are to use when it's in a complete solid state. So the first phase which is of interest to us is called alpha ferrite, alpha solid solution, or as I said popularly, it is called ferrite. uh, Students, see, we have already said that in any alloy system, solid solution is always going to get formed. And apart from solid solution, there may be a possibility that if some other type of phase gets formed, which is not a solid solution, then it has to be a chemical compound called intermediate phase. Interestingly, in your iron carbon system on the iron cementite diagram, 3 solid solutions get formed and 1 intermediate phase of the type interstitial compound gets formed. Now these first solid phase, the second solid phase, and the third solid phase, all are solid solutions. Specifically, these are interstitial solid solutions. Why interstitial solid solutions? Because in each of them, carbon is the solute, iron is the solvent, and because carbon has got a very small atomic size as compared to iron, it generally gets into the lattice positions. It does not get into the lattice positions, but occupies interstitial spaces, interatomic spaces, or voids in the unit cell of iron, and thus forms an interstitial solid solution. The only difference is, you can say, sir, if all are carbon in iron, then how are they different? It's the allotropic form of iron which is different in each of these phases. Here the solvent is alpha iron, here the solvent is gamma iron, here the solvent is delta iron. And this last phase which we'll discuss is not a solid solution, rather it's a chemical compound. It's an intermediate phase, transitional phase, and we know that interstitial or transitional phases are of 3 main types. This belongs to the first type. It's an interstitial compound or a size factor compound. So students, let's get started. Let's talk about these phases one by one. Ferrite. Students, ferrite is an interstitial solid solution of carbon in alpha iron. So it's a solid solution, it's an interstitial solid solution, carbon is the solute, alpha iron is the solvent. The maximum solid solubility of carbon in alpha iron is 0.02 percentage. It's a very small solubility, only 0.02 percentage is the maximum amount of carbon that can be accommodated in alpha iron, and that too happens at a special temperature. It happens at 727 degrees centigrade. If your temperature is different from 727, alpha iron cannot even accommodate, means ferrite cannot even accommodate 0.02 percentage of carbon in it. And one of the temperatures which is of great interest to you is the room temperature. Now if you talk about the room temperature, and if you ask me what amount of carbon is present in ferrite phase, the answer is 0.0008%. And if the temperature goes down to say 0 degrees centigrade, then the carbon solubility in this ferrite solid solution is just 0.00005 percentage. Let's come to the crystal structure. We know the crystal structure of any solid solution is the same as is the crystal structure of the solvent. So what is ferrite? Ferrite is carbon in alpha iron. What is the crystal structure of alpha iron? BCC. So what would be the crystal structure of ferrite? The crystal structure of ferrite is also BCC. Let's come to the properties. Ferrite phase is very soft and it is very ductile. It's the most soft and the most ductile phase that appears in the iron carbon system. Okay. Is ferrite phase magnetic or non-magnetic? See, ferrite phase from 0 degrees centigrade till 768 degrees centigrade is ferromagnetic or magnetic. 768 happens to be the Curie temperature of iron and also of ferrite. So beyond 768 and up to 910, till which ferrite generally exists, it becomes non-magnetic or paramagnetic. If you ask for some of the important mechanical properties of ferrite, you see ferrite has generally got a tensile strength of around 245 megapascals, yield strength of about around 118 megapascals, hardness of about 95 VPN, and as I said, it's the most soft and ductile phase which appears on the iron cementite diagram. Its percentage elongation or ductility on a gauge length of 5 centimeters is about 50%, which is huge. So students, now let's come to the second solid phase, that is austenite. Austenite, see, ferrite gets its name because it's nearly iron. Iron mane ferrite, Fe. So it hardly has any carbon in it, but whatsoever little carbon it has, that also brings about significant changes in the mechanical properties of this ferrite phase compared to pure iron properties. This phase, the most important phase of the iron carbon system, which is responsible for making steels, cast irons, which are alloys of iron and carbon, so versatile with such varied properties. Austenites, bachcho, we get this name because this phase was discovered by a scientist, Sir Austin. So after his name, to give honor to that wonderful personality, the phase was named after him, Sir Austin. Austin's name, austenite. Austenite is again a solid solution. It's an interstitial solid solution of carbon, but now in gamma iron. The maximum solid solubility of carbon in gamma iron is 2.11 percentage, and that happens at a special temperature of 1147 degrees centigrade. Even at a temperature of 727, the solubility of carbon in austenite or in gamma iron is huge. It's 0.77 percentage carbon. Okay, then let's come to the conclusion to be drawn is that the carbon solubility in austenite is significantly greater as compared to it was in ferrite, or it would be in delta ferrite, which we'll discuss just after a while. So austenite, now coming on to its crystal structure, it's again a solid solution. The solvent's crystal structure is FCC, gamma iron crystal structure is FCC. So austenite, which is a solid solution of carbon in gamma iron, its crystal structure is also FCC. The wonderful part is that the mechanical properties of austenite phase are very good. It's again soft. It's also again very ductile, not as ductile as ferrite, but significantly ductile. But what is important is that it has got good toughness and malleability also. The only problem with austenite is that because it's a high temperature phase, it's a phase with gamma iron as the solvent. Since gamma iron is non-magnetic, so austenite is also non-magnetic. The other problem is that since this is a high temperature phase, but it has got wonderful mechanical properties, how do we get it in the steel under room temperature conditions? So students, for that we have certain elements which are called austenite stabilizers. And if austenite stabilizers like manganese or carbon or even nickel, etc., are added to steels and cast irons, we will be able to make austenite stable in those alloys, and even at room temperature conditions, austenite phase can be observed in the steel. But that's a costly affair because the alloying elements that I've just named, nickel, etc., are costly. But like in materials like austenitic stainless steels, 100% austenitic microstructure can be seen even under room temperature conditions. But under normal conditions, austenite is a high temperature phase. It would be an equilibrium phase, a stable phase only under high temperature conditions in excess of 910 degrees centigrade. Also, this is a non-magnetic phase. I think I have already said that. Now coming on to the mechanical properties, some of the characteristic mechanical properties of austenite include that its ultimate tensile strength is about 1035 megapascals, its hardness is about 395 VPN, and its percentage elongation is about 10 centimeters on a 5 centimeter gauge length. We come to the next phase. This is called delta ferrite. Delta ferrite is one of the least important phases of the iron carbon system. Why least important? Because this phase gets formed in the temperature band of about 1400 degrees centigrade plus. And in physical metallurgy, because see, the most important tool that we use in physical metallurgy is the heat treatment. And while doing heat treatment, in none of the cases would we go beyond a temperature of about 1100 to 1200 degrees centigrade. Most of the heat treatment processes get completed in the temperature band of about 900 to 1000 degrees centigrade. So this phase would never appear when we are doing heat treatment of any iron carbon alloy. But why are we discussing it? Because during the formation of steel initially, when we melt the iron carbon system and we bring down to the room temperature, then in the range of 1410 to 1495 this phase would form, and it must be known to a metallurgist as to what is happening in the iron carbon system in that region, which is called the peritectic region. Now we come to a very another important phase, which is called iron carbide or cementite. So as I said, iron carbide or cementite. Okay, delta ferrite, whatever little information I have to give about delta ferrite is that it is an interstitial solid solution of carbon in delta iron. The maximum solid solubility of carbon in delta iron is 0.0 9% carbon, and that happens at a special temperature of 1495 degrees centigrade. So delta iron is a solid solution, interstitial solid solution. Carbon is the solute. Delta iron is the solvent. Maximum solid solubility of carbon in delta ferrite is 0.09% carbon, happens at 1495 degrees centigrade. So let's now come to the last and another very important phase of the iron carbon system. This is called iron carbide or cementite. As I said, this is not a solid solution, it's an intermediate phase. It's a transitional phase. Of what type? It's an interstitial compound or a size factor compound. So it's a chemical compound of iron and carbon which exactly contains 6.67% carbon and remaining 93.33% of iron in it. What is the crystal structure? Because it's an interstitial compound or a size factor compound, if you remember, the crystal structure is given by the Rx by Rm ratio. The Rx by Rm ratio for iron carbide is 0.63, which is more than 0.59. So it has got a complex crystal structure. The crystal structure is basically orthorhombic, which contains 12 iron atoms and 4 carbon atoms per unit cell. Coming on to the properties, cementite has got very high hardness. In fact, this is the most hard phase which is observed in the iron carbon systems. Its hardness is about 1000 VPN. 1000 VPN. It has got very high brittleness, which is a problem with cementite, and it has practically got zero ductility, another problem. It has got very high compressive strength, but the tensile strength is low. It has got good electrical conductivity, and it possesses metallic luster. It's slightly magnetic below 210. So Curie temperature of cementite phase is 210 degrees centigrade, and you will find a dotted line to signify this information. So cementite is partially magnetic below 210 degrees centigrade, and if the iron carbon alloy which is containing it is present at a temperature beyond 210, at a temperature higher than 210, then cementite becomes totally non-magnetic. The melting point of cementite is also very high, 1227 degrees centigrade. Another thing about cementite, students, cementite is not a true equilibrium phase. At whatsoever temperature it exists, low or intermediate or high, whenever it exists as a metastable phase. Metastable phase, as we have already discussed, means it is not a unstable phase that over an observable period of time it gets converted into some other phase, nor is it an equilibrium phase. Why isn't it an equilibrium phase if it does not break? See, it does not break before us over an observable period of time, but it has always an urge or tendency to transform into, dissociate into iron and graphite, because the free energy of that system is lesser than the free energy of a cementite system. But even at high temperatures like 700 degrees centigrade, that would take about thousands of years to happen. But because this has got this tendency or urge to transform into more stabler phases, the iron cementite is a metastable phase. And generally one question is asked in interviews, that is iron cementite diagram a true equilibrium diagram? True equilibrium diagram means that whatsoever phases under whatsoever temperature composition conditions which are being contained on the diagram are equilibrium phases. Answer should be iron cementite diagram is not a true equilibrium diagram, because one of the phases that it contains is a metastable phase. And who is that? That is cementite. So what should you say? You should say that iron cementite diagram is not a true equilibrium diagram, it's just a metastable diagram, because it contains cementite, which is not a true equilibrium phase. So students, that was all about the important phases that we see on the iron carbon system. And in the next session we will discuss about the iron carbon iron cementite equilibrium diagram in more detail. I hope you enjoyed this session. Thanks for watching.